Okay, so I've demonstrated a couple of times how the area under a curve gives us, area under a velocity time curve is giving us the distance. We need to, of course, be aware of a couple instances. Suppose we have some sort of curve above the x-axis, or the t-axis, I suppose, and we are evaluating from t1 to t2, then the distance is going to be the integral of that function evaluated from t1 to t2. Okay, because it's above the x-axis. The horizontal axis, we looked yesterday at the area between two curves. In this case, one curve is v of t, the other curve is y equals 0, or v of t equals 0. So that gives us the positive distance here. Now, if we see now that the curve is below the x-axis, or below the horizontal axis, then what we can do is the same kind of thing as what we were looking at yesterday. The distance, well, because we're going to evaluate from t1 to t2 of this function, is basically going to be 0 minus this, which will give us a negative distance, and we know that distance traveled cannot be negative. So we're going to stick a negative in front there to change this negative distance into a positive. So this is all gearing up to us using displacement and velocity. And so the integral of a velocity function is equal to the displacement. Okay, we were just talking about distance. That's if we knew kind of if the function was above the t-axis or below the t-axis. Sometimes we won't know just by looking at the function itself before graphing it if it's above or below the horizontal axis or not. So still the integral of the velocity is the displacement, and the displacement is then going to be s of t2 minus s of t1, which makes sense. The placement of the particle or the object at the second time minus the placement of the article or particle, at the first time. So the difference between those two places is the displacement, and that is going to be the integral of velocity with respect to time. So one thing that we're just going to be dealing with distance in a straight line. But in distance in a straight line, an object could go forward and then it could come back and it could go back again. And if we're trying to find all the distance, the total distance traveled, we can find the displacement fairly easily by just evaluating s of t at specific times. This could be time t1 and this could be time t2. So we could find the displacement, but then we have to add up this distance here plus this distance plus that distance to get the total distance, the final distance traveled by some final time. So if a particle or an object is moving back and forth, the velocity function could be some sort of a quadratic. And so the quadratic might look something like this, for example. And if that's the case, then when we take the integral, the distance traveled in these two sections would be positive, but the distance traveled in this section would be negative. So what we need to do is we would need then to take the absolute value. So if we want the total distance traveled, then what we can do is we can take the integral from t1 to t2 of the absolute value of the velocity function with respect to time. And what that does is it effectively takes this portion of the velocity function, and it flips it up so it's above the x-axis. So this all gets flipped up here. So then we're looking at the area under the curve where it's all above the x-axis, and then it all ends up being positive. Okay, so now that becomes positive. Okay, so that's how we're going to be looking at total distance. We can use this in our calculator quite easily, and that'll give us the final values. You can, of course, find the distance traveled from, say, 0 to the first time, and then from the first time to the second time, and then the second time to the third time, and then add them all up. Or we could just go from 0 to the third time with the absolute value and find the total distance. Okay, so now there's a few things that need to be found, or a bit of a process, that we need to follow in order to find the total distance traveled if we're going to do it by hand. So the first thing is we're going to draw a sign diagram for v of t so we can determine any changes in direction. Okay, so we want to know if it's positive or negative. The second thing we're going to do is we're going to determine s of t, the displacement function, by integration, including the constant of integration, because there may be some starting point that's not 0 for the particle. The third thing we're going to do is we're going to find s of t1 and s of t2, and then we're going to find s of t at each of the direction changes. After we do that, we're going to draw a motion diagram, and finally we're going to determine the total distance traveled from the motion diagram. Okay, so that's going to be the process that we're going to be following. All these steps and procedures will be put into action tomorrow in class when we look at our examples. In the meantime, to take a look at examples on page 484, 486, and 488, and then I would like you to glance at the assigned questions that I'll be asking you to practice on tomorrow in class. So please do that tonight after watching this video, and then tomorrow after we look at the examples, things will become crystal clear. So thanks for watching, and we'll see you in class.